Okay. So the next unit is going to be some applications of the differential equations that we just spent time solving. So we're going to start with an easy one, which is simple harmonic motion.
This just keeps popping up.
The worst thing is that we don't do the same thing for this.
So here's a spring. We're going to attach a mass to it. So here's your mass. The mass stretches the spring out. S, we'll say. And we call this position equilibrium. Without the mass. And the idea is that you can compress the spring with a force, and simple harmonic motion will give us some oscillation. And what we're going to do, at least to start, we're going to assume that we have a basic system with no damping. So we're going to use Hooke's law, as well as Newton's second law. Hooke's law, in case you've forgotten, force equals Ks. In other words, it's proportional to the stretch distance Newton's second law, which we've been using quite a bit, is force equals ma. We're going to go, in this particular unit, we're going to use the weights of the springs a lot, so we're going to go weight equals mg. And I will review this with you. The mass typically is going to be slugs for the units. And the constant for g is 32 feet per second squared. I think you already know kilograms and 9.8, but this is typically what will be used. I don't remember what it is. Okay, so now using both of these, so at equilibrium, we have mg, the weight of the mass, is going to equal Ks. In other words, we could say mg minus Ks equals 0. Now, when the mass is displaced, so if it's compressed upward, or if we pull it downward, okay, then what we're going to do is use force equals ma. And assuming that there's no other forces, then what we can say is that the total force, which is ma, it's going to be minus k and now we have to kind of think about this scenario here. If we stretch this out further, so if we pull this down, or we can do this one here, where we compress, okay, there's going to be the initial Ks factor plus this extra x distance from equilibrium. Okay, so if equilibrium's right here, and if we compress it x, or if we stretch it out x, okay, in addition to this s, we have this extra x piece. So this will also be added now with the original mg. Sorry. So essentially it's like what we have here at equilibrium, still same model, mg minus ks, except we have this extra piece of, depending on how far we pull it or how far we compress it. Okay. Now, let's see, what can we do with this? If we move some stuff around, since we also know that minus ks and mg are going to equal what? 0. Then all we really have left is ma equals negative kx, which is, I think, what you're used to. Which gives us the model if I move some stuff around and replace a with a differential equation here. So we have a would be second derivative of x with respect to t plus kx equal to 0. Or if we divide through by m, which we're used to doing, we get d squared x dt squared plus k over m x equals 0. So this is good, this is good. Sometimes we'll also rewrite these as d squared x dt squared plus omega squared x equals 0, because it'll be easy to write the solutions in terms of this nice constant omega squared. Again, where omega squared is k over m. What's that?
Angular velocity.
No, not angular speed. Okay. So now the general solution I don't know why I just crossed out solution. The general solution.
Just general.
So if we do x double prime plus omega squared x equals 0, and let's say we have some initial conditions imposed, like x of 0 is some constant alpha, and x prime of 0 is some other constant beta. We can go ahead and use these to write these in terms of alpha and beta, but in general, if we leave the constants in, what's the auxiliary equation for this?
M squared equals, well,
Which gives us what solution for x? For m, yes. So m would be plus or minus omega I. So what's the solution?
C1 cosine
Omega t.
plus C2.
Yep. So this is what we call the equation of motion.
don't think of it. Wait, wait, something cosine.
You mean sine, maybe?
It was both, but you could move the
Phase shift over? Or?
yeah, that's
Yeah.
what it was. So,
We're going to eventually write this in terms of sine. Just
Yeah.
one function. But for now, I mean, this is where it comes from. We have the auxiliary equation, which we talked about last unit, so this is what the solution is going to look like. One thing that we're going to make sure everybody is on the same page about, if we're talking about downward, that's going to be positive. Okay? If something is compressed or says it's pushed upward, we're defining x to be negative there. Okay. Let's see, what else do we need? The period of motion would be what? Two pi over omega. Frequency? Yep, just the reciprocal. Okay. All right, so this is the background that we need as far as setting up some models, solving some equations. Some of the things that you'll have to do in this particular section is, given an equation, describe what that equation might represent, or given a scenario, find the equation on your own and then solve it. Okay, so we'll do the easier of the two first. So let's say, for instance, that we have d squared x over dt squared plus 10x equals 0. And let's say that x of 0 is 5, x prime of 0 is 0. Okay. What is the solution going to look like? C1 cosine of, is it 10? Root 10 t. Well, yeah, I mean, you can, but because we know that that's what the solution is going to look like, right? Because it's in that format, m squared plus omega squared. So C1 cosine root 10t plus C2 sine root 10t will be the solution. And now, since we have these initial values, let's go ahead and figure out what C1 and C2 are. So we should probably find x prime as well. X prime of t will be negative root 10 C1 sine root 10 t plus root 10 C2 cosine root 10 t. What's that? Couldn't have been that stupid if you said it.
Just the ID 10T joke.
What's x of 0? Which has to be C1. X prime of 0 is 0, and that has to be root 10 C2, or in other words, C2 is 0. So for this particular model, 5 cosine root 10 t. So this is the solution. And let's go through all the details. Let's see. Period would be 2 pi over root 10. Frequency is the reciprocal. And now what they might ask you to do is describe what this could represent. So one possibility is that we have some mass, bless you, that starts where? 5 units below or above?
Below.
Good. Starts 5 units below equilibrium.
Can you scoot it a little bit?
Sorry. See, once I leave this, it's hard. It's been a while. Mass that starts 5 units below equilibrium with what velocity?
0.
So initial velocity is 0. And once it's let go, it oscillates back and forth. According to the equation that we just figured out.
So are the second lines more important?
Which lines?
The last two lines.
Yes, very, very much. In fact, you need to do it the same way or I'll take off points on the test. Mm-hmm. Okay, so if we graph it real quick, this one starts at 5. Period is what? 2 pi over root 10. So in that amount of time, it's... So it looks something like that. What's that? That's just a normal cosine graph, yeah. Okay. So there's your basic example. Here's a model. It represents simple harmonic motion. This is what it could represent. The other scenario is given some information, writing the model, and then solving it. So let's do that. Are there any questions on what we've done so far? Okay. All right, so let's say we have a 2-pound weight. That stretches a spring 6 inches at t equals 0. The mass is released from a point 8 inches below equilibrium. With upward velocity 4/3 feet per second. Find x of t. Okay. So, let's find out all the details. You want to find the mass. So if we know weight is mg, and we have 2 pounds for the weight, what's g in this system? 32 feet per second squared. So now the mass, if we divide, would be 1/16, and that is of a slug. Okay. You don't start with weights in physics?
No, it's
Well, now you know more. Now, we also should find the spring constant. You do that in physics?
yeah.
Okay. Force is going to equal Ks, K times stretch, right? So we have 2 pounds. K, what's the stretch? 6 inches. Let's keep everything consistent. So 1/2 foot. So the spring constant here is going to be 4. All right. Now, my advice is to use, where is it? This first one here. So we have all these different variations, right, of the same model. But when we're modeling stuff, it's probably easier to start back here, where you just do ma plus kx equals 0, because it's easy to just plug everything in there. Okay? So if I want to use m d squared x dt squared plus kx equals 0. Then I just replace everything. I get 1/16 x double prime plus k, which is 4x equals 0. Does that make sense? And then we solve. So you can multiply by 16 to make life easier if you want. What are the roots going to be for the auxiliary? Plus or minus 8i, so the solution, C1 cosine 8t plus C2 sine 8t. All right, and now let's use some of the information here. So back here when I wrote the model, I probably should go back and also label some of this given information. So we start 8 inches below equilibrium, so what does that translate to? X of 0 is 2/3, good, so convert that to feet. And then upward velocity, so x prime of 0 is, it's going to be negative 4/3. Upward is negative, downward is positive, so just make sure you remember. Okay, so plug those in. X of 0 is going to be 2/3, which is going to be from C1, right? X prime of 0 is negative 4/3. And that's going to be from, well, I didn't find x prime. X prime is going to be minus 8 C1 sine 8t plus 8 C2 sine 8t. So when you plug 0 into x prime, the sine term goes away. All that's left, oh, I messed that up. That should be cosine. All that's left then is 8c2 times 1. So then c2 is going to be negative 1/6. And there we have it. So the solution, x of t is going to equal 2/3 cosine 8t minus 1/6 sine 8t. Okay. So that's most of the section. The other parts will be rewriting this in a different format, finding times when it goes through equilibrium, which is just trig really, but we can do that real quick. So let's talk about that alternate form. Okay, the argument is that any function that's written like this can be written as just some a value times sine of omega t plus phi. Okay, so this is nice because if we have it as just a sine function, then we could find the amplitude. Whereas here we don't really know the amplitude just from looking at it. Okay. Now here's kind of the explanation for why this works. The idea here is that the a value is going to be the square root of c1 squared plus c2 squared. And then the phase angle can be represented by this right triangle here. So this will be the phase angle. So these are the assumptions that we're taking when we're doing this format. And if you're wondering why this works, okay, so how does this make sense? Well, take this equation, and if we use the addition formula for sine, you guys remember the formula for the addition formula of sine? Sine, cosine, plus cosine, sine, angle 1, angle 2.
What?
Maybe I should just write it here. Sine of s plus t is sine s cosine t plus cosine s sine t. Does that sound familiar?
That does sound
That's how
familiar.
you get the double angle.
Was,
Yeah.
was one of them like negative? Was
That was for
negative?
cosine, yeah. Cosine was cosine, cosine, and then that sine switches to minus, sine, sine. Anyway, if we use this formula from pre-calc, which now that we've reviewed it, we can use it, plug in omega t and phi as the two angles, then what we're going to get is A will distribute to both of the sine cosine terms, so it'll be A sine omega t, and then cosine phi, plus A cosine omega t sine phi. So then let's see, what are we left with? Well, we have A sine omega t, and if we use this definition for the phase angle, we could rewrite cosine of phi as adjacent over hypotenuse, because that would be the hypotenuse, right? So adjacent over hypotenuse would be c2 over square root of c1 squared plus c2 squared. Oops, sorry. Plus, yeah, and I think you guys see it. Same thing with cosine omega t, but now when we do sine of phi, that'll be c1 over square root of c1 squared plus c2 squared. And these little denominators were defined as A. So when you multiply this out, the A cancels with the A down here. Same with the second term. And all you're left with is C2 sine omega t. And then C1 cosine omega t. Okay, so this kind of explains why we can write this formula, which is typically what we're going to get for our solution, in this format here. Okay? So to finish example 2,
Could you just
sorry. So if we go back to example 2, and let's rewrite it. So rewrite the solution in the alternate form. Now it'll be easier to find amplitude when it hits equilibrium, okay? Because you can't really do that when it's written in terms of a sine and a cosine function, unless you graph it and do it graphically. But we may be working for a no calculator test this unit, so
No.
yeah. Yeah, and the last test really could have been one too, right?
Yeah, I don't think
I think half of you had it on your desk and you didn't even touch it.
No, but I just feel comfortable.
Yeah, it's like a
there.
comfort blanket.
Anyway, so let's find A. A will be, let's see, C1 was 2/3, so that'll be 4/9, plus 1 over 36, which is going to be 16 plus 1, so root 17 over 6.
See, this is something I would have used my calculator on.
Yeah.
No, like seriously.
You guys are silly.
I know.
What's omega in this case? For example 2? 8. So then really all we need, we have A, we have omega, we just need to find this phase angle. Okay? So, easiest way to do that is, do tangent. Tangent of phase angle will be C1 over C2, which is going to be 2/3 over negative 1/6. Okay, and this also gives away what quadrant this phase angle should be in. Okay, so think positive sign. And this represents cosine being negative. So what quadrant is that? Second. Okay, now for this one we will use the calculator. So if we reduce, what is that? Multiply by 6. That's just going to be negative 4, right? So do the inverse tangent of negative 4. And what do we get approximately?
Degrees or radians?
Let's do radians.
Negative
Negative 1.33 radians. This is like pre-calc all over again. But that's not the angle we want. Because 1.33 radians is in quadrant 4, right?
Just add 2 pi. Grab from pi.
So 1.33 would be here, negative, right? We want this one. So 1.33 is also here for the reference, right? So what would phi be then? There we go. Pi minus 1.33 approximately. Whatever that is. So if we take pi minus whatever the calculator gave you, you should get about, bless you, 1.8 something. 1.81. Okay, so then x of t is going to be approximately root 17 over 6 sine of 8t plus 1.81. And now once we have the equation written like this, you can answer any question. What's the amplitude? Root 17 over 6.
Or not.
Maybe not.
Not so
At what time or times would this mass go through equilibrium? How do we go about doing that? What would that mean in terms of this equation?
Wait.
I think it's like 8.
What does it mean? What does it mean to go through equilibrium?
X equals 0.
So this won't do anything. So maybe I should do that real quick. So when does it go through equilibrium? If we look at just sine 8t plus 1.81, that has to equal 0.
So negative
And here's our angle.
negative 1.81 over 8 plus the period.
Half the period, right? Because when is it going to be 0? Basically any multiple of pi, right? So as long as this angle is any multiple of pi, it'll go through equilibrium. Since this is a physical model, we can go ahead and say that k is typically going to be just positive integers here. And if we solve for t, then we can say pi k minus 1.81 over 8 with the same condition here. So this would represent all the times when this will go through equilibrium. Okay, things will get a little bit more involved once we start doing... Do we do damped tomorrow? Yes, damped. Forced is fun. Okay.
We don't do like potential or kinetic energy.
No, but we'll do an application with some circuits. Using Kirchhoff's law and...
Wait, circuits like electrode, like electricity?
LRC, inductors, resistors, and capacitors.
Is this unit like
I hate being that.
No.
how much is it?